Hello everyone, again we will start the next part in our nuclear chemistry topic. We have covered all the red topics here. Now we will talk about type of radioactive decays, half-lives, and I will show you some examples. Now, some types of radioactive decays, they are all in your reference table O. They name the decay, they show how to what kind of notation use, and what is the symbol for this decay. We have alpha decays, beta decays, gamma decays. Also, there might be, these are not decay, this neutron, proton, positron. There might be, these are the types of particles that may add it to the reaction, transmutation reaction, or removed from the transmutation reaction. And still we need to use these symbols and notations for it. So all types of decays and particle notations and symbols are summarized in table O when you need to use them. So all the reactions, radioactive elements reactions are also given to you in table N. For example, gold. Gold is, if it is 198 gold element, it's gonna go beta minus decay. Beta minus decay. How long does this decay take? 2.695 days. Okay, so you will go and check beta minus decay. What is beta minus decay? You will come here. Okay, beta minus decay means beta particle decay. It means it's gonna go through that reaction. So let's analyze alpha decay, beta decay, and gamma decay one by one. Let's start with alpha decay or alpha emission. We have parent nucleus. This is the initial radioactive element. And if it goes to alpha decay, it is going to emit alpha particles, which is 2 proton, 4 mass. 2 proton, you can say 2 neutron, because 2 plus 2, 4. That is alpha particle. Positive 2 means there are no electrons in these alpha particles. So after parent nucleus, parent element goes to alpha emission, it's gonna give off alpha particle and a daughter nucleus, which is a new element right now. It is a new element because there is a change in the proton number. Remember, each proton, all elements are unique because they have different proton number. Okay? So that is the common reaction. You have parent nucleus, proton number, mass number. If it is gonna give the alpha particle, you are going to subtract 2 from the proton, 4 from the, I'm sorry, I moved accidentally, 4 from the mass. What's the example? Example is uranium. It has 92 proton before. If it goes to alpha decay, you are going to remove 2, 92 minus 2, 90. You are going to subtract 4 from mass, 235 minus 4, 235, 1. So now you have 90 proton, and 90 proton is thorium element. It was uranium element, now it became thorium element, and you have 1 extra alpha particle. Quick way for a large atom to lose a lot of nucleons. That is how they explain the alpha particle. And the next one is beta emission. Again, you will start with the parent nucleus, your radioactive unstable element. It is going to give off a beta particle. Beta particle is negative 1 proton, which is interesting, right? And 0 mass. It's gonna give off a beta particle. That is how we write the general reaction. Let's talk about the example. Potassium 19 is a radioactive element. When it goes to beta decay, look at this please. You have 19 at the beginning. If it goes beta decay, it is negative 1. It means negative 1 plus 20 makes 19. That is how you figure out this 20, okay? So 20 proton number. 20 is calcium. If you go to periodic table, 20 proton, you are going to find out calcium element here. And look at the mass number. 40 initial, 40 plus 0, still 40. Identity of atom change. It was 19 potassium before. Now it is 20 calcium element. You create a new element. That is how new elements are formed. That is why we have so many different elements, because of this unstable radioactive elements, which is amazing. The last one is gamma emission, gamma decay. In this one, nothing happens to proton number 60, but you release energy. And these are the more dangerous ones. I'm going to show you what it means. Emission of high energy electromagnetic radiation usually occurs after emission of decay particle forms a metastable nucleus, does not change the isotope or element, because it's just energy. No proton change, no mass change. Next one, radiation energetics, alpha particles, relatively heavy and doubly charged, lose energy quickly in matter. Beta particles, much smaller and single charge, interact more slowly with matter. Gamma and X-rays, high energy, more length interaction with matter. So what does it mean? These are information how to protect yourself. If, for example, if there's a radioactive element and you know what type of decay it goes, for example, you have francium element and it goes to alpha decay. Okay, it goes to alpha decay. How are you going to protect yourself? What type of barrier you need? Okay, now since you know that's the alpha decay, alpha particles can be stopped by a paper. Even one paper can stop the alpha particles. If it is beta decay, you need something a little bit thicker than paper, like a thick plastic. If it is gamma and X-ray, now this time you need a lead wall. If it is neutron particles, you need a thick concrete. That is why in nuclear plants they have a thick concrete, because remember the fission reaction I showed you at the transmutation? Look what particles are emitted. The uranium emitted 3 neutron particles. For each one uranium element will emit 3 neutron, and that is why they have thick concretes to protect the environment from the radioactive decays. Okay, so the most dangerous one, neutron, gamma, beta, alpha. In the regions, they may not ask about neutron. They may only ask about gamma, because that is the only different one. These are particles. Gamma is only energy. That is why gamma is the most dangerous one if they ask in the regions. And that is the summary. Alpha emission, easily shielded, considered hazardous if alpha emitting materials is ingested or inhaled. Beta emission, shielded by thin layers of material, considered hazardous is a beta emitter is ingested or inhaled. Gamma emission, need dense material for shielding, considered hazardous when external to the body. Decay rates. Now, the decay rates, we use the time required for half of the sample to decay, and it is called half time. If you have 1 gram of radioactive material to decay to 0.5 gram, we call it half-life. For example, you have cobalt-60 radioactive element. At the beginning, it is 1 gram. After 5 years, it is going to be 0.5 gram, and that is the half-life. Okay. Copper 64 radioactive element. If you take 1 gram copper, if you wait 13 hours, you may end up 0.5 gram of copper 64 radioactive element, because it's gonna go decay. Let's check what type of decay it goes. We have copper. Where's copper here? Oh, there's no copper here. They didn't put the copper here. Let's go cobalt. It says 5 years here. Cobalt will go to beta decay. If you wait 5 years, you are going to have, it's gonna go beta decay, and half of it will be decayed. 1 gram cobalt will become 0.5 gram cobalt in 5 years. Okay, that's how the half-lives work. I'm gonna let's show it on this one. Half-life is the time required for half of a sample to decay. Imagine you have 12 parent isotope. Parent is the initial radioactive element. After one half-life, you will have 6 parent isotope, 6 daughter isotope. After another half-life, you are going to have 3, because 12 divided by 2, 6 divided by 2, 3. And you are going to form new elements after each half-lives. That is how half-lives work. And in the regions, you will use this table. If they ask, what is the half-life of hydrogen-3 radioactive element? You are come here, it is 12.31 years. And they may ask, what type of radioactive decay does uranium-235 go? That is the one that we use in the radioactive nuclear plants. You are going to say it's going to go to alpha decay. Okay? So these are how we find decay mode, half-life, and how we name it. That is gold 198. We are naming them with their mass numbers. And that is it, everyone. I will prepare regions examples in my new video. Bye.